Okay, let us start. Our recording is been started. That's good. So let us complete this question. The question is, a thin walled, let me do this, see. A thin walled double pipe counterflow. So the counterflow means the water enters here and leaves here. Sorry, this is hot oil. And the cold water comes here in a separate tube. They are not mixed together, but their heat is exchanged. So what happens? Heat. We want to reduce the temperature of this hot oil. So how can we reduce it? By introducing a heat exchanger. So this is a cold water line, and when the oil, this container is filled up with oil, and you want to reduce the temperature of this oil, so heat should be lost from the oil, and heat loss from oil equals to heat gained by water. So you remember the formula mc delta T, heat gain. But heat loss from water, let's apply this first law. First law, thermo. Okay, so energy in, I would say rate of energy in equals rate of energy out. Since it's a steady flow, in steady flow, the mass inside the container, it remains the same at any time, and energy of the container remains same at any time. And whatever we are putting, this is the inlet. Suppose this is 1, exit is port 2. So m dot h1, and on the right hand side we have m dot h2 plus heat out. The heat is lost, so I would say this heat is lost to the water, and water increases its heat. So now we are interested in this heat loss, q dot out. So q dot out equals to m dot h1 minus h2. And now if you take a look here, the oil has a specific heat capacity. So that is delta H equals to Cp delta T. So I can write down here m dot, this is for oil, okay? Oil, m dot Cp T1, T2. So what is m dot in our case? So 140 at a rate of 2 kilograms per second. So m dot for oil, this is for oil. So this is 2 kilograms. The oil has 2.2, okay? 2.2 kJ per kg K, and T1 entering temperature is 150, leaving temperature is 40. This is 4, okay? So if you solve for this, do you get 484 kilowatts? Please make sure you get the same number. Sarah says 484. So let's write it down here, 484 kilowatts. And as I mentioned earlier, whatever we are losing heat, the same heat is being transferred to water pipeline. Okay, so can I write down, because in the end, what we are trying to find out, determine the rate of heat transfer. That's what we have already found in the heat and the exit temperature. So we have found the heat transfer rate, which is 484, and the exit temperature. So for water, the next thing which we have to find out, exit temperature of water. Suppose this is 0.4, this is 0.3. Okay, now what is the exit temperature? So can I write down heat gained by water? So mass flow rate is given. This is 1.5 kilograms per second. And the specific heat capacity for water is 4.18. 4.18. T4 we have to find out. T4 at the exit temperature. And inlet temperature is 22 Celsius. 22 Celsius. It's the same heat. So if you do the math, do you get 99.2 Celsius? If you get the same answer, then the answers are verified. Please do the math and help your professor. LC says 99.2. That's good. Sarah says the same. That's good. Okay, guys, now we have done this question regarding the heat exchanger. So make sure you prepare for the heat exchanger problem and go ahead and prepare for this lecture, last week lecture or last lecture, which we covered about a few problems, and do the homework problems. So this chapter is complete. So I'm gonna give you the quiz next week from this chapter. And let's go and start our chapter 6 now. So in this chapter, we are going to learn about the heat engine and the efficiency of the heat engine. So let me go over to this chapter. So the big picture, if you go to the first lecture, if you remember the first lecture, so let me go over to this first lecture a little bit here. I alluded to you about the first law of thermodynamics, and then I found I gave you some diagrams, did I? The big picture which we're gonna understand in this chapter, I want to show you. So if you have a heat engine, or refrigerators or air conditioners, so and we draw the diagram of heat engine with a like blocks and circle, and similarly we will draw the diagram of a refrigerator or air conditioner like this. It's just a big picture before I go into the slide by slide. So what happens that heat, this is high temperature, this is called source, heat source. This is high temperature. This is the sink. This block means sink. And this is the uh, process, the work done, work output. And heat travels from hot body reservoir to cold body reservoir. And once it is channelized, if we have to make a channel, once it is channelized to flow in a certain direction, then we get the work output in terms of like moving certain blades or piston. And this is the work output. So the work out equals to the Q at high temperature, Q at a low temperature. This is heat at a high temperature. This is heat at a low temperature. And on the other hand, for the refrigeration cycles, so the heat, this is sink, this is QL, this is QH, this is QH is at high temperature, QL is at a low temperature like evaporator. So we have to work in like a compressor. We have to apply the external work to move the heat to flow from the cold body reservoir to a hot body reservoir. So the source outside, the source is actually the condenser or and sink is an evaporator. So the thermal efficiency of the heat engine is the work out and divided by the heat supplied. So the work output can be written as the difference between the heat supplied minus heat rejected. So this will be in the numerator and the denominator is the heat supplied, and you get this final answer 1 minus QL over QH. So this is how you find out the efficiency multiplied by 100.